the kind of disclaimer that, I mean, this is going to be a talk about the Fukaya category, and it's a case in which the Fukaya category, I find, is somewhat less fascinating than the cases which I like to think about. On the other hand, there's still some subtle points which I think make this subject somehow still interesting. So that. So first of all, definition is that M, I, J, K, G is a hyperkähler manifold, and see that the board here is going to be tricky to manage. Okay, if well, I, J, K are complex structures on M, and G is a Riemannian metric, which is a Kähler metric. For I, J, and K simultaneously. So okay, well, in this case, we immediately get omega I is G of, say, I. So this is going to be a symplectic form. And similarly, omega J, omega K, symplectic forms, real symplectic forms. Okay, and then just for some comparison with what we had earlier, we can define, say, omega I with a capital omega will be, say, little omega J plus I little omega K. This will be a holomorphic symplectic form. It's an I holomorphic symplectic form.
So you need also to ask for quaternion relation.
Oh, sorry. Yeah. I squared equals J squared equals, yeah. I mean, oh, yeah. Okay. Ij equals K maybe, and Jk equals I, and Ki equals J.
And also opposite, yeah? So it's okay.
Is that enough, or? Yeah, I mean, maybe you have to say, maybe you can derive all the ones from that. I'm not an expert on what the minimal set of relations for the quaternions is, but anyway, thanks.
It's enough.
There's 3 dots there to be absolutely safe. Right. So what are the examples? Well, one example is if say M omega is a compact holomorphic symplectic manifold, then the Calabi-Yau theorem and some other machinations imply that M is actually a M has a hyperkähler metric, and then you can go and actually construct the I, J, and K. So M is hyperkähler. I'm not going to say how you exactly get those, but actually you don't have to be compact in order for this to this to happen. So for example, all of the Nakajima quiver varieties, you can think of them as arising by a hyperkähler quotient, and then you get a hyperkähler structure on them. And this is, hyper hyperkähler. Okay, so that's why we might be interested in this kind of thing, at least in this conference. And, well, the main thing which you study in the Fukaya category is what you call J-holomorphic curves. So J here is a little bit confusing because we have a J in the definition of hyperkähler. So let's call it theta instead. So theta, let's say it's an almost complex, or let's say almost complex structure on M. Okay, so this means that just that theta is a sort of map from the tangent bundle of M to itself, just a C infinity automorphism of the tangent bundle that squares to minus the identity. And that's it. So it doesn't necessarily come from a complex structure on the manifold, because you might not have coordinates that, trivialize this sort of multiplication by I in some neighborhood of a point. But so this is a more flexible sort of notion. Then let's suppose that sigma and J is going to be a Riemann surface. Okay, which might not be compact, and it might have boundary. Possibly not compact. Possibly with boundary. And so then we can talk about a map from U. I have a feeling this is a bad place to write. So I will now erase. So U is called theta holomorphic. This is a definition. If theta composed with du plus du composed with little j is equal to 0 on sigma. So that's a sort of PDE you can write for a map between manifolds. And these things play an important role in the Fukaya category. I have to explain how in a few minutes. But let's say what happens for hyperkähler manifolds, and why these turn out to be not quite as interesting as you would think in that case. So let's assume now that sigma is obtained from a compact Riemann surface by removing a finite set of points, a finite set of boundary points. So sigma is going to be a compact Riemann surface with boundary. So that means that it's say a two-manifold with boundary, a real two-manifold with boundary with a complex structure on it, and I move some of the boundary points. Z is a finite set. So, for example, there was a reason. Sorry, Andre. Well, right, so for example, sigma could be something like this. Maybe like a little hole here, and then a little boundary here, and a little boundary here. And then in addition, maybe just remove some boundary points like that. Okay, that will be my sigma. And well, now let's talk about, let's see here. Let's assume that, okay, yeah, let's suppose that H is a Riemannian metric. I need one more thing to say. On M, maybe not related to any of the other metrics we've been talking about, so not related to G, for example, then you can find the energy with respect to H of U, for that matter, any map, is just going to be the integral, maybe I should say this explicitly. So let's say U is a map just maybe not holomorphic or anything, like smooth. Then you can define the energy of this map with respect to H to be the integral over sigma of U star. Sorry, I want to say like this: du du H volume sigma. Okay, and this thing a priori depends on a choice of a metric on sigma, but it doesn't really. So I'm going to just omit that. So here you're just looking at this thing as a map and measuring its size using the metric on H and using a metric on sigma, but then you also use the metric on sigma to define the volume form, and these two dependencies cancel out. So this is a well-defined thing, only depends on a metric on M. So now, what do we want to say? Well, one more piece of information. Okay, so let's suppose now that Li are Lagrangian submanifolds, say with respect to for omega I. Okay, in particular, they're going to be I holomorphic. They're I holomorphic submanifolds, so they're actually they're preserved by this complex structure I. This follows, I think, from the Lagrangian condition. If not, I'll assume it. Then let's assume that, let's consider now U from what do I want to say? Well, let's call this set how do I want to say this? Right, I'm going to number. So sigma I are going to be just the boundary components of sigma. So in particular, this would be like, shoot, is there colored chalk here anywhere? Alas. Oh well. Do without colored chalk. So this here would be like B sigma 1. This here would be B sigma 2. This could be B sigma 3. And so on. So if you took out a boundary point, you get more boundary components. Okay, so now let's consider U that is theta holomorphic, and such that U of d sigma I is contained in Li for all I.
So M is hypercarrier, or
M is hyperkähler, yeah. I mean, this definition, of course, didn't use hyperkählerness, but
Theta is an additional structure on M, or was
theta is still just an arbitrary, almost complex structure until I state the theorem, and then it's going to be specific something. So now I think, so with the theorem, oh, I just need one more piece of notation. Let's say that Ri is equal to the set of all Ai plus Bj, such that A squared plus B squared is equal to 1. Okay? So this is going to be, I mean, topologically this is a circle. It's a collection of of complex structures on M. Okay, which are kind of, no, I said the wrong ones. Aj plus bk, that's better. So it's just sort of a circle which is, well, kind of orthogonal to I. And, well, the theorem is, with Misha-Verbitsky, and various versions of this are known to many people, so I don't claim much originality here, is that for all but countable theta in Ri, any U is above with, so the crucial thing is that the energy has to be finite. Sort of in all stories having to do with J-holomorphic curves, you want to look at finite energy curves. So if you look at all U which have finite energy and satisfy such boundary conditions, it must be constant. Okay, so that means that basically J-holomorphic curve theory on these manifolds is apparently fairly not interesting. I'll try to convince you that nonetheless, this is something which is worthwhile knowing. And perhaps along the line of Davesh talk, it's possible to do some kind of, if you do fix a theta, one of those countable theta for which this statement fails, you can definitely hope to get some interesting enumerative problems out of that, but I'm not going to talk about that today. Anyway, let me try, why is this useful?
You have an explicit description of the theta?
This theta? Yeah, it's completely explicit.
What is it like roughly?
Sorry? What is it like roughly? Well, I mean, I could just prove this theorem on, well, depends how, do you really want to hear anything about the proof of this theorem before I explain why it's useful? Probably not.
I think Davesh's question
I mean,
was what is that set of the set of
right, so I mean, you can use, Okay, if I give you any homology class and homology relative to these Lagrangians, then you can consider what you get by integrating the omega associated to theta. So it's going to be a symplectic form associated to theta. You can integrate that symplectic form over that homology class. And you can look at that as a function of theta, as theta moves around in a circle. And you just want to exclude those theta for which some homology class makes that function hit a maximum. Okay, so of course, number of homology classes is countable, and each one has a unique maximum. So that's the proof of the theorem, basically. You just exclude all the possible theta for which you get a maximum on some homology class. Now, I mean, I should point out that maybe the reason why this isn't a completely trivial theorem is because I didn't make any assumption on these Li. So in particular, they might intersect in some pretty horrible way. And in particular, it's not even clear that a finite energy theta holomorphic map represents a homology class. You could definitely have cases, even finite dimensional, say Morse theory or something like that, where you look at like a gradient flow. Think of a holomorphic curve as being a gradient flow of the action functional. You could have a gradient flow which approaches some kind of singular critical set of a function and just goes round and round and round and never converges to anything. Okay, so the fact that actually any such U has to represent a homology class requires some non-trivial kind of properties of, well, I guess it's really belongs to like subanalytic geometry or something like that.
Sorry, so Li are fixed at the beginning?
Yeah, well, I mean, it doesn't matter. You can just take any, you just have a bunch of boundary components, and then you so yeah, I mean, the countable set depends on the choice of the Li.
That's what I meant.
And in particular, for closed surface, this applies.
Yeah, this applies for closed surfaces for sure. Yeah, that's like an old result of Michel-Verbitsky. So I think the interesting analysis here is to show that, for example, U actually represents a homology class, and then show that once it does represent a homology class, the integral of some form over it only depends on that homology class. Those are sort of not entirely trivial statements.
Say if I move Lagrangians, this set doesn't move, or is it like if isotope Lagrangians will stay the same, or is it
If you isotope the Lagrangians, well, if you isotope them all at once, then it will stay the same. But if you move one and you don't move the others, which is the kind of thing you usually want to do, then of course the set will change. But I mean, in general, you don't expect to have any isotopes of a holomorphic Lagrangian, right? I mean, if you take a Hamiltonian flow and you apply it to some holomorphic Lagrangian, it's going to stop being holomorphic pretty fast. That's, yeah.
So is sigma is fixed? The complex structure on sigma is fixed, or is it for countably many for all possible?
Okay, so it doesn't matter which, this countable set does not depend on the complex structure on sigma.
Yeah.
So for any possible complex structure on sigma, this countable set will be the same countable set. You can just avoid that countable set and you're good. So if you want to integrate over the whole moduli space of Riemann surfaces, that's fine.
So this means that if you take a generic complex structure on the hypercalic manifold, choosing a generic point from this two-sphere.
From the circle.
Or maybe from two-sphere, then it's not going to have any holomorphic curves.
Right, so this argument requires you to look at specifically that circle. I mean, I guess if you're, I can't say.
I'm talking about closed curves.
Oh, closed. Oh, yeah, that's sure. Yeah, definitely. For closed curves, then, yeah.
Do you have control over how the homology class changes as you pass through one of these bad points, or?
How the homology class.
I mean, or is it just
The homology class doesn't
It's
change.
fixed, okay.
I mean, what will change is the Foucault category. Okay, so as you move theta through a bad point, interesting things will happen with Foucault category. There'll be some non-trivial, although the objects will be the same things, there will be a non-trivial kind of A infinity equivalence of categories, which goes from the one defined with respect to theta, so I say quasi-equivalence, between the one defined for theta and the one defined for say, theta prime.
And is that that circle inside the sphere? If I go away from that circle, then what?
Then I don't know. I don't have much to say. I really want to look at that circle because otherwise, somehow the symplectic forms you associate to a theta which is not on that circle will no longer make these Li Lagrangian. Okay, so omega j and omega k vanish on it because this thing vanishes. But then if I take some, if I add some multiple of omega I, then I have no idea what happens. It's going to actually, I know exactly what will happen. It's scalar with respect to omega I, so it's just going to stop being Lagrangian and completely disappear. So I don't know if this even makes sense so much.
So are we supposed to think of this real locus as like Roma had this picture, like a real locus inside the complex locus and some special points on the real locus? Are we supposed to
Real locus?
he had like a complex space of stability condition, like real space of stability condition, and some special points in the real. Is that
Do you think this Ri has something to do with the real locus
I
of
don't know.
Roma's?
I'm just,
Maybe.
okay.
I don't think this is. Yeah, is this? Yeah, obviously these could be thought of as having to do with stability conditions, but yeah, it could be related. I'll have to give that to you. So anyway, why is this useful? So the main thing I want to do is talk about the Fukaya categories. This is going to just be like a pedestrian introduction to the Fukaya category, and hopefully along the way there will be some kind of fairly trivial remarks, which so floor homology and the Fukaya category. And I'm going to specialize to the case that we're interested in. So let's assume a whole bunch of things about M. So I'm not going to necessarily assume that M is hyperkähler, but I'm definitely going to assume that it has a trivial canonical bundle. So we're going to look at, so from now on, M omega is some symplectic manifold, real symplectic. Okay, and we're going to look at, did I decide to change to using, just want to get my notation, yeah. Okay, right. So theta is going to be an almost complex structure. Right. So this is some almost complex structure. So we said that what that is already, but we're going to assume now that it's omega compatible, which means that shoot, this was supposed to be a G, by the way. Should have caught me on that. It has to be, yeah. So that means that G theta, which is equal to omega of, say, theta and stuff, no, other way around, is a Riemannian metric. And for future use, which hopefully will be made of use of, so this is going to be a set of all omega compatible almost complex structures. This is a contractible space, an infinite dimensional contractible space. So then we're going to assume there exists, and we're going to fix some kind of phi, which is going to be a complex valued differential form, which is of type n0, with respect to theta. So this is essentially some kind of Calabi-Yau condition, but I'm not assuming that it actually has some kind of Calabi-Yau metric or anything like that. Now, we can look at L.
So it's not non-vanishing?
Yeah, non-vanishing, thanks. So Li are going to be just a Lagrangian for little omega, and let's say I here runs in some index set, and I'm going to assume that Li intersect Lj is clean. So in other words, the tangent, no, I have to, I mean, I want to assume this for if B is some subset of A, so let's denote by LB is equal to the intersection of Li. So then we're going to assume that everything intersects cleanly. So that means that the tangent space to LB, the intersection of a whole bunch of them for any B, is equal to the intersection of the tangent spaces of the Li. Oops. All right. So in addition, in order to define things, I have to choose a couple extra structures here. I'm going to assume that choose a spin structure on Li. And also, let's choose grading on Li. So that's going to explain a bit. By the way, I could get away with a relative spin structure, if you can guess what that is. If not, then just assume it's a spin structure. So a grading on Li is, well, a choice of theta Li from Li to R, such that the when I restrict my n0 form phi to Li, I get e to the I theta Li, okay, times some rho, where rho is just a positive form on Li. So I'm assuming that the Li are I mean, they're spins, so in particular they're oriented. So I just assume this, well, rho is positive. Okay, as a positive n form.
So this is not, you assume that it exists?
It's a choice if it exists, and I'm assuming that it exists. Yes, it doesn't always exist. Yeah, so we're going to assume exists. Okay, so once we get all of that, then we can start to define the floor complex. So yeah, so if, I don't know, P smooth manifold, I'm going to say that A star P means differential forms. On P, So then if I take some C inside of Li intersect Lj, say a connected component, then I can define Cf star Li Lj subscript C to be just the differential forms on Li intersect Lj shifted by MC and tensored with the Novikov field, which I forgot to define. So let me just say what all this stuff means.
So these clean intersections means that the intersection will be smooth?
In particular, yeah, the intersection will be smooth. Yeah. So this means in particular that Li intersect LB is, say, L smooth. Or I could just say LB is smooth, but all I need is Li intersect Lj. I mean, that was kind of by fiat, because, I mean, I was trying to say that, yeah, the tangent bundle here exists and it's equal to that. So in particular, it's smooth. Right, so MC here is a Maslov index of C, which is defined using basically elementary topology and these gradings theta Li. So any connected component, you just assign to it an integer MC, and lambda is the Novikov field. Which is given by all sort of formal sums. Here AI are, let's say, real. Yeah. And the EI are also real. And we're just going to assume that the limit as I goes to infinity of EI is equal to infinity. Okay, and the t is just some formal variable. And this thing comes with a valuation, I should say a norm. I decided to use a norm. So the norm of a non-Archimedean norm is equal to the what I want to say, exponent of minus the minimum over I of so if this thing belongs to lambda, so then this limit is infinity, so the minimum exists. I can take the minimum of EI like that. This defines a non-Archimedean norm. And of course, this tensor product is completed. All vector spaces are completed with respect to this norm. We'll no longer mention that. So we get a norm, of course, also on the Floor complexes. Now, in general, we can define Lij, and I'm probably out of time already. No, not yet. Is supposed to be equal to sum over C, Cf, C. Okay. That's how we define the morphism spaces in the Fukaya category. So, I mean, I haven't said yet this is a category, but at least we've defined for any two Lagrangians some vector space.
And the two Lagrangians could actually be the same Lagrangian.
For example, because all we did was assume that you have clean intersections. That's why I'm doing that, just to allow to get the same in Lagrangian, which is kind of a very important case. Now, let's suppose that I fix some multi-index where the I, say, P belong to A. Okay, so now I want to talk about M, I, and let's suppose that, what was my notation again? Shoot. Yeah. Okay. So now M, I, E. This is going to be a space of theta holomorphic curves. So probably want to say a little bit more about this before I go on. Right. Yeah.
I didn't understand. So this depends on this component C that you fix, but you play differential forms on the whole intersection each time?
Oh, sorry. Of course, that was supposed to be C. Thanks. Yeah, please ask questions if I make obvious mistakes. I mean, and even if I don't make obvious mistakes. I'm sure I'm making lots of obvious mistakes and lots of non-obvious ones too. So, yeah. Now, let's say that okay. If I take, so I'm going to have a bunch of points z0 up to zk. They're going to be points in the, this is going to be a closed disk. And here is going to be the, in the boundary of the closed disk. And this is going to be the pairwise diagonal. And
Is that the dimension of the disk, or is it copies of
k copies of the disk. Okay, so then I'm just going to take this thing in this, okay, and z will just be sort of like the union from 0 to k of zi, which is a subset of the boundary of the disk. As opposed to okay, and also we can talk about this zi plus 1, which is going to be a interval in the disk. Well, in the boundary of the disk. So if I have the disk that has a complex orientation, and that induces an orientation on the boundary, and let's say the orientation on the boundary goes counterclockwise, so then if this is zi, then this is zi plus 1. Right, these guys are always ordered according to the orientation, ordered with orientation of the disk. And sort of this is the interval zi plus 1. Okay, because it goes from zi to zi plus 1, and not the other way around. Okay, so now I can define this space. M, I, E is going to be, by definition, the set of U and Z such that U maps the disk minus Z to M, and it maps the interval, so I get this right, I, Z, I How do I want to do this? Zi. Okay, definitely going to confuse this, but
Zi minus 1 I to Li.
okay, let me just copy. Z. Yeah, it's always a question whether it's I minus 1 or I. That's what I'm always confused about. This goes into Lij. There we go. And of course, I mean, like when I get k plus 1, I mean 0. K is the number of marked points here. So, and I want also the energy with respect to g theta of u is less than infinity, and I want, sorry, it should be equal to E. Yes, it has to be U as 3 theta holomorphic. With respect to, of course, the standard complex structure on the disk. And anything else I need to add here? Yeah, that's about it. Okay, so the first thing you want to do with these guys is define evaluation maps, very much like in Davish's talk. So we can define, all right, so it's a fairly standard lemma because of the cleanness of intersection that U extends continuously to U bar from D to M. Okay, and all right, so then I can talk about valuation maps of I from M I E to Li, which take a pair like this and send it to U bar of Zi. Okay, this should be intersect. Let's get this right now. Lij minus 1. Like that. Okay. Now, then I can, if I have, say, given, say, C equals, say, Ci0 up to Cik, where the Cij belongs to, sorry, is a component of Li. Let's see what it should be. J minus 1 intersect Lij. We can define just MICE is equal to the intersection of J inverse of C. I should have said C. Well, I should have said just C1 up to CK. That makes more sense. CJ. Okay, there we go. FCJ. Very good. Which is a subspace of this guy. Okay, and now I can try to define the operations on the Fukaya category. Well, just so we see where we're going. So define, now I'm going to do something fairly evil. Define mk right, mk from cf c1 say L0 Li0 Li1 tensor up to CF Li k minus 1 Li k, and here is going to be C k, and this one is going to take CF C 0 L I 0 L I k shifted by 2 minus k. Okay, that's going to be defined by so if I'm given a bunch of, say, differential forms here, alpha 1 up to alpha k, then mk of alpha 1 up to alpha k, maybe I should give this a superscript c, is going to be given by, well, the main thing is t to the, I want to give this a subscript e, just so I remember where it's coming from. T to the e of 0, push forward, this is the evil thing, of 1 e, pull back, alpha 1, up to of k. That, sum over e, greater than or equal to 0. Oh, I forgot to say what stability means. And all about, shoot. Nothing whatsoever. I mean, no. It's the same thing as in Devesh's talk, but much, much worse. But yeah, I mean, so I should have said, yeah, I mean, I kind of neglected when I defined these MIE to A, quotient by automorphisms, and B, say that I'm looking at stable guys. So I should have, I mean, omitted stable, which means that, okay, maybe I'm just going to skip writing this down for now. And if somebody really wants to know, then I'll, what?
And this is a countable sum, actually, yeah?
And this is a countable sum, yeah, by Gromov compactness.
So there are only countably many values of e for which this is non-zero.
That's correct, and they converge to infinity. So this actually makes sense in the topology we defined. And here we put just one little thing, which is if, and this is kind of like in Davesh's talk, there was a cup product followed by all sorts of quantum corrections. Here, what we're going to do is when k is equal to 1, we're going to just put in by hand the de Rham differential. So d here is the, we'll just take from, say, C1 to itself, well, by degree. This is the exterior differential. Okay, so then, right, given what Roma said, this push forward here has to be interpreted with a great deal of care. And of course, well, I mean, the pullback as well, because we don't even know what kind of space this is. But it can be done, much like what Davesh was saying, by looking at our manifolds as being modeled by some kind of zero set of a section of a vector bundle over some kind of finite dimensional space, or maybe infinite dimensional space if you prefer, depending on your tastes. But in any case, somehow the Fredholm index of that section will always be finite dimensional. Well, that will always be finite. So it's going to be a Fredholm section of some bundle, perhaps over a polyfold or something like that. Well, I don't really have time to say anything very intelligent about this, or even not intelligent about this today.
So this will be an A infinity category?
Right, so the point here is that we can define mk to be the sum of, so mk is going to now map
Jake, if you allow all sorts of derived kind of stuff here, why insist on clear intersection of Lagrangians in the first place? Maybe you can, is there some,
because I don't actually want to, I mean, maybe this is a discussion for after the talk.
Okay.
It's a bit technical. I want to finish saying what this thing actually gives you. So, and make a couple extra remarks just before I run out of time. So here this is from IL0, 1, etc. IK minus 1, IK, 2. Okay, is given by, you know, mk is equal to the sum over c of mk c. Okay. So then what we have is that the sum of mk 1 plus of, say, alpha 1 up to alpha q minus 1 m alpha q to alpha q plus k2 minus 1 alpha q plus k2 alpha k. Okay, this thing taken with appropriate signs, minus 1 to the, say, star, is equal to 0. So this means that essentially this thing what should defined as an A infinity category. Well, I should just mention that mk is defined also for k greater than or equal to 0. So this is not a standard A infinity category, but a curved A infinity category. And I guess m0 is the curvature. How's it defined? By the same formula. Just, I mean, there's nothing to pull back, so you just push forward the fundamental class. You push forward, I mean, the product of the empty product is just 1. So you just push forward 1. And, you know, in the case that you, for example, have a discrete moduli space, then you get, right, I mean, I forgot to say that I was compactifying and all this business. And so I wrote down an open stratum of this thing. What I meant to do was to A, quotient by automorphisms in the stable case, and then compactify using stable maps. I just omitted that from the lecture. Now, one thing which I think is useful to remember is that so this is not going to really happen in any of the cases which are interesting for us, as Davesh was saying, but it still does happen in lots of interesting cases. It's a special case. Suppose you have M is, say, like a homogeneous space. And then, say, L is the real, say, a complex, you know, homogeneous space, something like, you know, G mod B. And then L is, say, the real points, which is, you know, let's assume this is defined over R, so you choose some real involution. and L's the real points, then actually all these modular spaces are in fact smooth. And they can be constructed essentially using algebraic geometry. And the evaluation maps are all going to be submersions, which are proper. And so in fact, all of these things make sense in just completely elementary terms. And then an exposition in that setting can be found in a recent paper of myself and Tukaczynski from 2016, and there we just kind of go and prove like these relations and every other possible property you might want to know about these in that setting, just so that there's some reference down, which you can see that done. And I think really all you need to know is just basic algebraic geometry to get that in full detail. So I'm going to stop here, and the next time I'll say.